Welcome to our E&M project. So, in our world, electricity is everywhere. It powers so many things. It's just a basic component of life, whether it be from cars, to lights, to our very important thing, our phones, and to even random things like anime, like a Doctor Strange, or whatever the hell this is. But electricity is very important, and one thing with electricity is wireless charging, and this idea that we don't actually have to plug things in, and we can just transfer it across air. And so our group thought this was really cool, and we decided that, hey, let's just make a wireless charger. And there's a very big catch to it. But yeah, wireless charger. So how does it work? So first, we were going to make this really elementary system with two solenoids and a light bulb. And basically our idea was you move the solenoids together, and the light bulb it gets brighter because current, magnetic field, and induced current. So we start off with this. We made two solenoids, threw them together, connected to a light, and no light. So then we added two batteries, still no light. We made a very well-coiled electromagnet, still no light. So at this point, we were like, what's going on? And we realized this is a big no-no. So we're trying to get DC to DC, but we need AC current. So we came up with a new plan. We convert our DC to AC, and then AC back to DC.
We'll begin with a basic overview of how our wireless power transfer works. The first part of our wireless power transfer circuit takes in a direct current and converts it to an alternating current. This conversion is done with a Colpitts oscillator circuit. The key component of our oscillatory circuit is the inductor, represented by a rectangle in the animation. When current flows up through the inductor, the magnetic field lines are as follows. However, if we change the direction of the current, meaning it flows down, the magnetic field also changes. This means that by running an alternating current through our circuit, and hence an alternating current through the inductor, we can generate a changing magnetic field. A changing magnetic field is significant because of Lenz's law, which is given by the following equation. Then, by generating a changing magnetic field, and hence a changing magnetic flux, we can induce an EMF in a receiver coil, almost completing our wireless power transfer. The only thing left for us to do is convert our alternating current in the receiver coil back to direct current. This is done via a rectifier circuit, and one key component in a rectifier circuit is a diode, which we will discuss in greater depth. Diodes are formed by the union of two semiconductors, one of which is positively charged and the other of which is negatively charged. The positive side of the diode is called a p-type, and the negative side an n-type. Initially, attractive forces between oppositely charged particles near the junction of the two semiconductors results in electrons from the n-type section venturing into the p-type section. This creates a zone known as the depletion zone, with its own electric field. Now, if we connected this diode to a voltage source such that electrons flowed into the diode through the right, we would expect the electrons to power through the diode, completing the circuit. However, we should note that if the voltage of our voltage source is less than the potential difference created in the depletion zone, the electrons will not have enough kinetic energy to pass through. If we flip the flow of electrons, the positively charged particles will be pulled to the left of the diode, and the negatively charged particles to the right. This will create a stronger depletion zone and prevent the circuit from being closed. Hopefully you can see why diodes would be useful in converting alternating current to direct current.
Our Colpitts oscillator consists of two parts, an LC circuit and an amplifier. We'll start with the LC circuit. Everyone here should be familiar with this one. As a charged capacitor discharges, it charges up an inductor's magnetic field, which forces current to recharge the capacitor on the other terminal even after it has discharged zero potential energy, perpetuating a sine wave. The formula for this oscillation can be derived using KVL. Plugging the formulas for voltage in a capacitor and an inductor, we get the differential equation of a sinusoidal wave with an angular frequency of square root of LC. This frequency is called the natural frequency, since it is the frequency the circuit naturally oscillates at. However, it is also called the resonant frequency, meaning that any alternate magnetic forces, or signals, received by the LC circuit at this frequency are absorbed as alternating current with the highest efficiency. An intuitive explanation for this behavior is an analogy to a swing. If you time your pushes on a swing at the exact moment it reaches the peak of its motion, you can increase the magnitude of the swing in the most efficient way possible. The computational explanation is impedance, the AC version of resistance in DC currents. Impedance depends on both the resistance as well as the reactance of any electrical components that react to alternating currents, such as capacitors and inductors. The impedance of inductors and capacitors both depend on the frequency. This implies that at a certain frequency, the impedance of the inductors and capacitors will cancel each other. And what is this special frequency? You guessed it, square root of LC. Now, why does resonance matter? If we use the same LC circuit in both our oscillator and our receiver, we can transfer power at the most efficient frequency. So we're done with our oscillator, right? All we have to do is charge the capacitor once and let the circuit run its course. Unfortunately, that is not the case. Due to the resistance in the inductor and capacitor, the original charge on the capacitor dissipates quite fast. To maintain the alternating current, we need to satisfy the most basic criteria of an oscillator, called the Barkhausen criterion. The gain in the oscillator's feedback loop must be greater than or equal to 1, and the phase shift of a signal around the loop must be a multiple of 2 pi. In English, this means that we must add an amplifier to the LC circuit that takes the output of the LC circuit, multiplies it, and feeds it back into the LC circuit so the oscillators are no longer damped. In the case of Colpitts oscillator, we use the common emitter amplifier. The common emitter amplifier is based on an NPN transistor, an electrical component made from 2 diodes attached back to back, with the N layer sandwiching a P layer. Every BJT has 3 terminals: the base, emitter, and collector. Just like in diodes, the depletion region prevents a flow of electrons between the terminals. However, when we apply a small current or voltage to the middle P layer, it allows for a much larger current to flow in from the collector terminal to the emitter terminal by creating a bridge of electrons in the P layer. With the basics down, we can now move on to the full circuit. Tracing the circuit from the power source, we see that our current is immediately split into 2 paths. The path on the left goes into a resistor voltage divider that provides a biasing voltage to the base of our transistor, which is a voltage that stabilizes the operating conditions of a transistor and ensures that it will amplify input signals. The path on the right feeds into a resistor that determines the maximum current going to the collector. During every oscillation of the LC circuit, it sends a weak signal back to the base of the transistor. We purposely weaken the feedback signal with a capacitor voltage divider that feeds into ground, since having too large of a feedback can cause distortions in the signal. The weak signal is then amplified and fed back to the LC circuit through the collector current. The current at the emitter terminal is simply fed into the ground. You might be wondering why there are 3 random capacitors sprinkled around our circuit. These capacitors are bypass capacitors, which are capacitors placed in a circuit for the sake of preventing the flow of DC current while allowing AC current to pass through. Esteemed classmate Samuel Joe enlightened me on the physics of this phenomenon with the following demonstration. When DC current flows through a capacitor, it hits the terminal. However, when AC current flows through a capacitor, it can sneak around. And that's it. Here's our oscillator simulation in action.
So now, we want to determine the efficiency of our LC tank circuit, which we can do by calculating the experimental and theoretical inductances of our solenoid. For the Colpitts oscillator, the frequency of the oscillator circuit and the equivalent capacitance of capacitors C1 and C2 can be used to determine the inductance. Through these calculations, we obtain a value of 0.00023 henries. But how would we find the solenoid's theoretical inductance? Well, I'm glad you asked. For a long solenoid, inductance can be approximated by this formula, where mu0 is the permeability of free space, n is the total number of turns, a is the area of each loop, and L is the total length of the solenoid. We can actually derive this formula quite simply using what we've learned in class this year. Using Biot-Savart's law, we show that the magnetic field produced by a solenoid is mu0 mini n times I, where mini n is big N divided by L. Next, we know that Faraday's law for a solenoid yields negative n times d phi over dt, where phi is the magnetic flux. We can rewrite the change in magnetic flux as follows by plugging in the above formula for the magnetic field of the solenoid. Doing so yields A mu0 Ni, which we then plug back into the EMF equation. The first term of the final equation is the self-inductance of the solenoid, which we can then use as an approximation. Doing this, we get a theoretical inductance of 0.016 henries, which results in a percent error of 98%. And while the percent error isn't great, it provides a foundation for future research to optimize our circuit's design.
So to measure our AC current, we use an oscilloscope, which is like, 1.4K free delivery though. But we use an oscilloscope to basically measure our current that we're getting in our solenoids, which, as you can see here, changed when we added phones. And here's just another situation where the current keeps changing and our graphs change, which goes to show that we're actually getting current in our solenoid and it's inducing a current. And here's actually when it worked. Like, as you can see, we're moving the stuff, and yeah, we were kind of monkeys. But there were some basic issues like, phone safety, voltage drop, and the voltage regulation we needed for a phone. So this is where the catch comes in. So basically, in order for voltage regulation, we need to use a wire. So we basically made wireless charging with a wire. But yeah, there were a lot of learnings that we took away, starting with AC and DC current, LC tanks, how to interpret circuit diagrams, and just a lot of things with the rectifier and regulation circuits. But there's a small problem. There's mechanical stuff. So we made a wireless charger with cooling. Okay, it's not that bad. I'm just
And now for my next number, I'd like to return to the classics.
Wait, ready? Our thing, and hypothetically, yeah, boom, bada bing, bada boom.
The wrong way,
Yeah.
bro.
Okay, fine, the other way. Okay.
We're gonna do this, and then cut to a scene where he plugs it into an actual charger, so you get the phone charging.
Academic dishonesty. All right, that's.